this lossless or else we're going to have problems. That means sigma 0 and epsilon double prime is there. And here we can have some loss. We can have some sigma, some eta, some mu that is not free space, but it doesn't matter. When we have a wave coming in and hitting, we know we're going to have a reflected field, right? We're going to have some E reflected here, but we're also going to have some E transmitted. Do y'all remember this from last time? It's just like when you dealt with transmission lines. Some of the stuff, some of the voltage that hits, that voltage waveform is reflected, some of it passes, right? So the key thing is knowing what the reflection and transmission coefficients were. I got it down, I kind of solved it fast last time for reflection coefficient. But in general, reflection coefficient or the ratio of the reflected field, by the way, this can be complex, to the incident field is given the symbol gamma, it's the reflection coefficient, right? The reflection coefficient is equal to, and it's fairly straightforward from here, it's always the impedance you go into, so it's eta 2 minus the impedance you came from over the sum. That's it. Yes, sir.
Will we always get either the impedances or the gamma?
Well, you have to have enough information so you can solve the problem. So either I give you the impedance, or I give you a frequency and the intrinsic impedance, or intrinsic parameters.
Okay.
But there's only one way to know. You have to have enough information to solve this.
Yes, sir. I just didn't know if we would, like, I didn't know there was another way to get gamma, or we're always going to solve it.
Well, you're going to have gamma, and you're going to have the intrinsic impedance, right? I mean, but those are all, once you have frequency and you know the material, it's a done deal. All right, anyway, and for the record, I think we all know that, but eta in general is the square root of j omega mu over sigma plus j omega epsilon. That's the total formula. And in general, gamma is alpha plus j beta equal to the square root of j omega mu times sigma plus j omega epsilon. And I'm just putting those up there as reminder notes for everybody, just so you know, right? And that should be burned in your mind by now, because you're going to use it so often. Okay, now getting back to this thing, there's also something where we take a look at the ratio of the transmitted field to the incident field. I can prove this, but it's just equal to 1 plus the reflection coefficient. And I want to say one thing. This assumes normal incidence. Which Wentworth would probably say, you didn't know you could have abnormal incidence. No, it's a mathematical term. It has nothing to do with happening. What it means is normal is when it's coming at 90 degrees. So if a wave is propagating this way and it strikes the wall so that it's at a 90-degree angle to the plane of the wall, that's called normal incidence. Oblique incidence is when the wave is coming in at an angle and it reflects off at an angle. Do y'all follow me? Where that angle's not right. We're going to get to oblique, but right now this is all for normal incidence, or call it, sometimes I put that down, the perpendicular incidence. It doesn't, this formula right here will not work for non-normal incidence. I'm going to tell you that. So anyway, if we do the math on this one, we put 1 plus eta 2 minus eta 1 over eta 2 plus eta 1. And this is equal to something called the transmission coefficient. All right, that tau, yes, sir.
With this eta 1 and eta 2, these eta, there was, whenever we were going through problems, or I was going through a problem, I noticed like eta 1 would be like an assumed value or something.
If it's air, it's 120 pi.
Okay, but if it's air,
All right.
that's what I couldn't figure.
Y'all hear me on this class? If you're in air or free space, it assumes sigma 0, u relative and epsilon relative are 1, and therefore when you do just crank the handle on that, it comes out to 120 pi ohms or 377 ohms, okay?
Yes.
And that number will come to you all the time. the ratio of E to H in free space down here for a propagating wave is it's 1/125. Okay.
Thank you.
I mean, of E to H is sort of 125. So anyway, this is the transmission coefficient, tau. Now, there's a way to write tau that I like better. Tau is equal to simply 2 eta 2 over eta 2 plus eta 1. The way I get it is, suppose we get a common denominator here. We'd have eta 2 plus eta 1 plus eta 2 minus eta 1, so 2 eta 2 divided by eta 2 plus eta 1. Do y'all see that, class? That always works. Now, I just got done with the powers. I told you the power is always going to be 1/2 the magnitude of 8, 1/2, or the magnitude of E squared divided by 2 times magnitude of eta times the cosine of that eta, right? And then it's e to the minus 2 alpha z, and it's in the AZ direction if it's a plane wave propagating that way. Remember that because people forget the cosine all the time in velocity stuff. Just warning you, that's a typical mistake. Now, back to this thing, when I have it. Y'all see with this problem, there's a lot of things that can happen. I just want to explain. I'll give you this. I'll show you in a problem. Everybody's used to starting here. I've got an incident field. I know the intrinsic parameters of the media. I know the frequency. I'll get the impedance and then the propagation and attenuation constant, right? Well, that's a forward solution starting here. What if I give you the transmitted electric field, or better yet, the transmitted power at a certain depth? Do y'all follow me? Now you would have to reverse engineer it back if I wanted to know what the field strength was that struck it. Do y'all follow me on this? But the way you always get this is, go for what you know. You know the equations, right? With me on this? So I know that over here in region 1, if I have an E field that's losses, that's the E field at the surface, right? Now let's give an example. Suppose I had the E field, transmitted E field, all right, transmitted E field, and I'm going to say I have that field quantity. I'm just going to give you this field quantity, the magnitude that's transmitted at the surface. Make it simple. Say it's 10 millivolts per meter, okay? And now I'm going to make my life easy. I'm going to say that eta 2 is equal to 40 pi, and I'll leave it as just 40 pi. And I'll say eta 1 is 120 pi. And what I want, so I've given you these things, I've done the calculations for you. By the way, looking at this, what can you tell me about eta 1 and eta 2? There's no wrong answer.
Eta 2 is there.
Is there any loss? Is there any loss, class? How do you know there's no loss? You're right. There's no angle, right? If there is no angle other than 0, right? If it's either the J0, you know it's lossless. So you check that box, right? And if the angle was 45 degrees, then you would know it'd be a very good conductor, wouldn't you? Y'all with me? So in your mind, you go through the math on this one. Take a look at this. That's the transmitted field. Now, the next thing logically you do, because you got that, is get the reflection coefficient, which would be eta 2 minus eta 1 over eta 2 plus eta 1. So eta 2 minus eta 1, 40 pi minus 120 pi, over the sum of those two, which is 160 pi, right? Right, and you probably are ahead of me on this one. So I can see the pi's cancel. Then I can see one of those zeros cancel. Then I have 4 minus 12 is minus 8 over 16, right? Correct? And that's going to be what? Minus 1/2. Check me on that. Y'all with me?
Would it be negative 80, 40 minus 120?
Yeah, and that's, it would be what? If minus 80 over 160 is minus 8 over 16 is minus 1/2. Do y'all agree with me, class? All right, so I got that. What's the transmission coefficient? Well, it's 1 plus the reflection coefficient, right? Y'all with me? So you can see that is equal to 1/2, right? Now I got the transmission coefficient, correct? Y'all see this, class? I want to make sure everybody can see. Now that I got the transmission coefficient, I know that is the ratio of E naught transmitted to E naught incident, correct? I gave you E naught transmitted at the surface, didn't I? Right? So, therefore, E naught incident is what? Well, what is it? It would be what? E naught transmitted divided by tau, or E naught transmitted divided by 1/2, right? Or it's simply equal to 20 millivolts per meter. Do you agree with this, class? Everybody? What's the reflected field, anyone? We know this is equal to E naught reflected over E naught incident, right? So we've got 20 millivolts per meter, right? As the incident field. What's the reflected field?
-10.
Minus 10, right? All right. Now, you are smart people. Can you all see how to get the power? It's lossless, right? So if I want the power density transmit, I'm going to write it right here if you don't mind. If I want the power density EF transmitted, right here, this is going to be transmit, it would be 1/2 magnitude of A to 2 times magnitude of E naught transmitted squared, right? Time, do I need to write the cosine of the angle there of A? Why not? You're right.
It's lossless.
Huh?
It's lossless.
It's lossless, so the angle's 0. Cosine of 0 is 1. Forget that. Technically, we should put e to the minus alpha z, but if it's lossless, alpha goes away too, doesn't it? Right? Alpha is 0 as well, which is really getting nice. This is an easy one. And then you put it in the direction of propagation, which is az. Now, look, we don't have to do this one, but can you all see E transmitted is known, right? I gave that to you as 10 millivolts, so it'd be 10 to the minus 2 squared over A to 2, which is 40 pi divided by 2. That's it. You all see this, class? I don't need to turn the crank on that. How many see how you could get the incident power density? Just give me a show of hands. All right, what would the incident power density? Do you, I mean, if you don't, do you see it or not? No? All right, what's the incident power density here? In general, what would it be? 1/2 magnitude of the incident field, right, squared, over magnitude of A to 1, right? Do I need to put a cosine here of the angle? Why not? It's lossless, angle is 0, cosine of 0 is 1, right? Do I need to put an e to the minus alpha or plus alpha z? Either one? No, because alpha is 0. And it would be, and this is going in the positive az direction, right? Now, you all see E naught incident was 20, I think, right? 20? So I take 20 millivolts, square it, divided by 2, A to 1, and A to 1 is 120 pi. Yes, sir.
So you put it 801 because it's on the
Yes.
first.
Power is always going to, power flow always has to do with the intrinsic parameters of the region it's in. Never the region it's not in. Does that make sense? So this is power density, I should say. You with me on this? All right. Now, you got 801. You can do this, can't you? The reflected power is the one I want to make sure you see. What direction is the reflected power going? That way, right? Remember that. It's going the opposite way. So, if you, I'll do it. I know where I'm not supposed to write. Heaven forbid that I violate that. My line of death. All right. Now, think about it. What is the P average reflected? Now, I'm going to level with you. Technically, we can put a minus sign in front of it. All right? I don't like doing it that way. I like putting a magnitude and an arrow saying it's going in the negative direction. Do y'all follow me on this? Because I hate to put a negative power value. To me, there's a lot of reasons why you don't do that, because it assumes that power is being sucked from the region instead of just being reflected from it. This is a long story, but, so when I talk about P reflected, technically, it would be 1/2, right? It's the magnitude of the reflected field squared. Then it's the magnitude of eta 1. And it would be in the minus AZ direction. Now that's absolutely correct. The minus AZ say it's flowing in the negative AZ direction. Do y'all follow me? I want to make sure you all understand. It's going in the other direction. It's bounced off. But here's the way I like to do it. Make that a positive and just say it's flowing in the minus Z. Okay? Now, if you put minus that plus AZ, fine, but I prefer putting plus AZ and say it's flowing that way, all right? Or put the minus there. I do not like the minus sign the way some people do it, because there's some ways you can misinterpret that. Y'all follow me? Everybody okay with that? All right. I'm going to give you a quiz now. Now, here's what I want you to do. Stop before you. First, the quiz is closed book, closed notes, no phone. So, what I'm going to do is ask people to populate the first row there. So you have to get up. You can take the first seat, and you can take the second. Get that. Try to leave this one open. All right. Now, here, like you can. I tell you what. You can stay.